Okay, in the screencast, and this is the last one, I'm going to show you the math involved in the titration of a weak acid and strong base. Again, it's very similar to the strong acid, strong base, but in this case, you have to keep in mind that in case of strong acid, you have complete ionizations, whereas in case of a weak acid, it's going to be only a partial dissociation. So let's say you have 25 milliliters of 0.100 molar acetic acid, and you're titrating it against 0.100 molar sodium hydroxide, which is your strong base. So your overall reaction is going to be CH3 COOH plus NaOH, which gives you CH3 COONA plus H2O. And so this is aqueous, this is aqueous, this is aqueous, and H2O is your liquid. Now, again, recall for the case of a weak acid, strong base, it kind of has like a little bit of a buffer region. It starts out high as far as the initial pH goes. The point of inflection is shorter, and but the shape overall is similar. So if you had to draw, let's say, if you had to draw strong acid, is going to probably start somewhere over here. Point of inflection will be deeper, and then it's going to move like that. So the first thing that you should do to begin your calculation is by determining the volume required to reach the equivalence point. This is what we did in case of our strong acid, strong base titration as well. So in order to do that, so again, what we are trying to do is we are trying to determine the volume of sodium hydroxide, which will give you the equivalence point. So I want you to calculate the moles of acetic acid that you have. And that's going to be just the volume times the molarity. Volume should be in liters, so 0.025 times molarity is 0.1 moles per liter. So liter and liter will cancel off, and you're going to end up with 2.5 times 10 to the negative 3 moles of acetic acid. Okay. Now, you know that at equivalence point, you will need the same number of moles of NaOH as the moles of acetic acid. That means at equivalence point, that's the rule of equivalence point, moles of acetic acid are going to be equal to moles of sodium hydroxide. That's when that color changes pink. So you would say, well, I have the moles of acetic acid, right? And if I use these moles to be equal to moles of sodium hydroxide, I can convert the moles into the volume, because I know the initial concentration of the sodium hydroxide solution that I have been provided with. So you'll say 25 times 10 to the negative 3 divided by 0.1, which is going to give you 0.025 liters sodium hydroxide solution. That means if you would have added 25 milliliters, that would mean that you have achieved your equivalence point, or you can say that equivalence point occurs at 25 milliliters, or when 25 milliliters of the base has been added. All right. Now, hopefully you can realize, just looking at this graph also, that the volume at the equivalence point of an acid-base titration curve, it does not depend on whether the acid being titrated is a strong acid or a weak acid. It depends only on the amount of the moles that are present, not on the volume that you have. So just realize, that's something to keep in mind, especially for the upcoming lab. All right, let's now take one step forward. Let's go one step forward and try to determine, now that we know, and I'm going to write this somewhere, 0.025 liters is what I need of NaOH, is what I need for equivalence. And now I'm going to try to determine the initial pH, that is before adding any base, after adding a little bit, that means when you get the buffer, and then after the equivalence point has been surpassed, we're going to take a look at that. So the exact same 4 locations as we did for the previous case. That's what I'm going to do now. Now, before you have added any base, the only thing you have in there is acetic acid, right? And that acetic acid is going to react with water, and it's going to go through a partial ionization and give you hydronium, and it's going to give you the acetate. Now, you can, this is aqueous, this is liquid, this is aqueous, this is aqueous as well. Now, you can determine the pH of the solution, because realize in case of a pH metric curve, on the y-axis we have the pH, and on the x-axis we have the volume of sodium hydroxide that is being added. So we really are looking at this point where no sodium hydroxide has been added. And realize that you can determine the hydronium ion concentration simply by an ice problem. The only reason why you cannot use the fact that you have an initial concentration of 0.1 molar for the acetic acid, but you can't just take 0.1 and take the negative logarithm of that, is because this is a weak acid. Yes, you got that right. So initial concentration is given. We don't have any hydronium or acetate. Let's say X moles undergo dissociation. That would mean X of the hydronium and X of the acetate will be generated. So at equilibrium, you would have X and X of the hydronium and the acetate. So Ka is going to look like X squared divided by 0.1 minus X. And of course, you're going to use the approximation. So X is really small. So you can just simply say X squared divided by the initial concentration is going to give you your Ka. And Ka for acetic acid is 1.7 times 10 to the power of negative 5. So you can say that X squared is equal to 1.7 times 10 to the negative 6. And when you take the square root of both the sides, you can say that this number comes out to be 1.3 times 10 to the negative 3 molar. And when you take, this is X, so when you take the negative logarithm of X, you're basically taking the negative logarithm of the hydronium ion concentration. And for that matter, the pH is going to come out to be 2.88. Recall, we have done this previously. We have calculated this previously for a different setting altogether. So you know now that your curve is supposed to start not at 1, not at 2, but rather 2.88 or 2.9 when no sodium hydroxide has been added. Okay, now we are told that at 25 we would have reached the equivalence point. So it's in between that we have to figure out. So let's consider what would happen if I have added 10 milliliters of sodium hydroxide. What would that look like? Now realize we are adding 10 milliliters and the concentration is 0.1 molar. So the moles that we have added is going to be the volume times the concentration. So we have added 1 times 10 to the negative 3 moles of hydroxide into the system. Now, what does this hydroxide do? This hydroxide is going to react with the acetic acid and it's going to form water, and acetate is going to get generated in the system. So now the question is, well, how much acetate will be generated in the system? Realize your initial, before the addition of the sodium hydroxide, your initial number of moles that you have was 2.5 times 10 to the power of minus 3. That's what you began with, right? And we have added 1 times 10 to the power of minus 3 of the hydroxide. That means after addition, hopefully you can see, since we still have more of acetic acid, hopefully you can see that 2.5 times 10 to the negative 3 minus 1 times 10 to the negative 3 of the acetic acid is still going to remain. So that gives me 1.5 times 10 to the negative 3 moles. And in that process, how much of the acetate will get generated? Since the stoichiometry is that 1 mole of hydroxide gives me 1 mole of acetate, then 1 times 10 to the negative 3 moles of hydroxide will give you that many moles of the acetate. So I have here the generation of a buffer where I have a common ion acetate, common ion with respect to acetic acid. So basically I have a weak acid and the corresponding conjugate base with respect to it. And so now if I wanted to determine the pH of that system, I can simply use the Henderson-Hasselbalch equation, and that will be pH equals pKa plus log of base divided by acid. And the Ka value was what, 1.7 times 10 to the negative 5th, and so the pKa value for that comes out to be 4.77 plus log of the base concentration is 1 times 10 to the negative 3. The acid concentration is 1.5 times 10 to the negative 3. Realize I'm using the numbers for moles as is because it's all within the same volume. So even though the base and acid are molar concentrations, I'm using the moles as is because it's all within the same volume of solution. So the volume and volume will cancel off. And so now you basically just solve this. And of course 1 divided by 1.55 will be 0.66. Let me just change the color just to show you the math for that. So this part is 0.66, and when you take the log of that value is a negative value, so I'm writing 4.77 minus 0.176, and you're gonna end up with 4.59. So realize again that for the first part, when we had not added any base, we had 2.37, and now we are adding sodium hydroxide. After adding 10 milliliters of it, the pH has risen, and so this is that part. This is the buffering part of the curve. Now we have already done A, which is what we found was 2.88. B we found it to be 4.59. We are going off to C and D. Those are the next two things that we have to determine. Suppose we have added 25 milliliters of 0.1 molar NaOH. Now this is the equivalence point because we calculated this previously, that once I would have added so many number of moles, all of the acetic acid would get converted into the conjugate base. That means CH3COOH is not going to stay as the acid form. It's going to get converted into CH3COO minus. And so if you had to sort of go with the same reaction that we had seen previously, where hydroxide reacts with the acetate and you generate, or acetic acid rather, and generates the acetate. You would say that you have in the system 0.0025 moles of acetic acid, and you have added 0.0025 moles of hydroxide, and in the end acetic acid basically gets exhausted. All of it gets converted into 0.0025 moles of the acetate. So realize that in this particular situation, the solution is no longer a buffer. That means it doesn't contain significant amounts of both the weak acid and the conjugate base. Instead, it contains only the conjugate base, which is going to be weakly basic, which is why you say that that acetate would be able to react with water and carry out this backward reaction to generate acetic acid and a little bit of hydroxide, which is why we say that such salts, sodium salt for example, is going to be alkaline in nature. So all of those concepts are basically they do hold true. Now if you had to calculate your pH at this particular point, the equivalence point, you will say that, well, I know the moles of acetate, and I began with 25 milliliters of acetic acid, and I have added 25 milliliters of sodium hydroxide. That means the total volume is 0.025 plus 0.025, and when you work out the math for this will come out to be 0.05 molar is the concentration of the acetate. So now that you have the concentration, the initial concentration of the acetate, and basically realize that we are utilizing the backward reaction, because that is going to generate the hydroxide, and if you know the hydroxide, you can envision an equilibrium problem, an ice problem, and be able to get the hydronium ion concentration from there. And if you have hydronium, you would be looking at the pH. So my equation, my equilibrium in question is this one in red. And I have an initial concentration for acetate, which is 0.05. Of course, there's no acetic acid in the beginning. There is no hydroxide in the beginning. If minus x in goes through hydrolysis, x of each is going to get generated. And so going through the stoichiometry one more time, acetic acid x moles, hydroxide x moles, and acetate is 0.05 minus x. And so you can determine the Kb in this case. You can set up a Kb as x squared divided by 0.05 minus x, and of course that x will be small, and that will be equal to Kb. Now, of course, if the value of Kb is provided to you, you can use it, straight away. On the other hand, if it is not, and only Ka is provided, is there a method you know that you would be able to determine Kb? Please say yes. Ka times Kb is Kw, right? So if you know the value of Ka, you know that Kb is going to be equal to 1 times 10 to the power of minus 14 divided by 1.7 times 10 to the power of minus 5. And that comes out to be 5.6 times 10 to the power of minus 11. So this value is 5.6 times 10 to the power of minus 11 x squared over 0.05, because x we cancelled, it was too small. X comes out to be 1.7 times 10 to the power of minus 6. But what was x? X was hydroxide. So if you take the negative log of this number, you're going to determine pOH, subtract that from 14, and that will give you pH. On the other hand, you can divide this number by, or rather, 1 times 10 to the negative 14 by this number to get the hydronium ion, and just take the negative log of that number. That will be your pH. Let's take a look. So since I have the hydroxide and hydronium times hydroxide is equal to 1 times 10 to the negative 14, and hydronium is equal to 1 times 10 to the negative 14 divided by 1.7 times 10 to the negative 6. That comes out to be 5.9 times 10 to minus 9 molar. And when you take the negative log of this number, 5.9 times 10 to the negative 9, it gives you a value 8.23. That means the pH at this point C is 8.23. It's alkaline, and that tells you something. It tells you that our assumption that we began with, that acetate goes through that hydrolysis, it rips off a proton and generates the hydroxide, is actually true. Now the last part is when you add more than the equivalence point. So what happens at, let's say, when you have added 30 milliliters of sodium hydroxide, how would we go about that aspect? Let's take a look. Realize that if you add 30 milliliters of 0.1 molar NaOH, you basically have added 3 times 10 to the power of negative 3 moles of the hydroxide. That means now you're going to have the hydroxide in excess. So going back to your original equilibrium for the neutralization that we were discussing, when you don't add, you start with 0.0025 moles. This is 0, and hydroxide is 0 as well. On the other hand, when you do add the hydroxide, how much have you added? You have added 0.003. And so after addition, what will remain is going to be only the hydroxide in the system. You will have 0.0005 remaining, and all of the acetic acid would have gotten converted into the acetate. And so the solution now is just a mixture of the weak base acetate and a strong base sodium hydroxide, and the strong base completely overwhelms the weak base. So if you had to calculate the pH of such a solution, you're going to consider the strong base alone, and hydroxide concentration can be thought of as 0.0005 divided by, we had 25 milliliters from the beginning, we have added 30, so overall it becomes 0.0091 molar. And you can then calculate the hydronium ion concentration by simply dividing 10 times negative 14 by this new number, which will be 1.1 times 10 to the negative 12. And now if you take the negative log of that, the pH will come out to be 11.96. That's the point D, where the point of inflection has already occurred and what you have in the system is overwhelmingly the hydroxide in the system. So if you recall, if you realize, the concept is the same between strong acid, strong acid, strong base titration, and weak acid, weak base titration. The only one thing that we have to think about is this region, which is the buffer region, and hence it is going to follow the HH equation. Rest everything else, the way we calculated, was either an ice problem, or it was basically utilizing the Ka times Kb equals Kw, or the fact that the pH plus pOH adds up to 14. All right, that settles this chapter, and the next screencasts will now start discussing chapter 17.